Thanks everyone for coming. I'm gonna start. So this is higher order functions and function ref, and today I'm gonna talk to you about this standard proposals that is likely to be in C++20 and general use case for higher order functions. First of all, if you don't know me, a little bit about me. I'm a software engineer at Bloomberg. I work in the new London office, and I'm part of one of the biggest infrastructure team that deals with the maintenance and adding features to the company's microservice framework. And it's all C++, some C++ 98, some C++ 17, 14, so it's mixed, but it's really challenging and really fun. I also do online courses. These are some I publish with Pact, and these are video courses about C++ standard library features and type-safe interfaces like using variant and optional effectively. And I also experimented with game development in my spare time. I did this a few years ago. I did create a few games and few video tutorials that you can find on YouTube for free on how to create your own games. And I also have a blog where I write posts about crazy, esoteric metaprogramming stuff. And recently, I've also been bitten by the bug of the standard committee. So I started going to meetings, writing papers, and trying to be more active in that aspect as well. Finally, you can find a lot of my libraries and projects that I do in my spare time on my GitHub page. And also, I like going to conferences, giving talks, and you can find them on YouTube as well. And that little box over there, I'm also one of those weird people that likes to answer questions on Stack Overflow. Cool. So what are we going to talk about today? We're going to talk about higher order functions, what they are, and some use cases and implementation techniques. Then we're going to go to the second part of the talk, which is going to be about function ref. And this is a proposal that I've been writing. And I'm going to tell you about the motivation, how it is specified, user examples, how you can implement your own, and then finally benchmarks. And this is a disclaimer. This is not a talk on functional programming. I don't have anything against functional programming. I really like it. But it's not always possible, to start a code base using monads everywhere and doing crazy, cool functional pipelines. So if you've seen Wampe's talk yesterday, it was really, really good. But I feel like you need to start with the intention of using those data structures and those paradigms in the first place. This is a little bit more, let's say, practical if you have an existing code base and you want to start using some of these ideas in order to make it better without changing the entirety of the code base. We're also going to look at, as I said, practical use cases and also existing functional facilities in the language and the standard, and then how you basically design and implement a proposal for the ISO meeting. I'm making some assumption here. I hope you're somewhat familiar with lambda expression, templates, and modern C++ features, but please do not hesitate to ask questions. So, higher order functions. Let's go to Wikipedia and see what it says. It's actually a very good description in my opinion. It just says that mathematics and computer science, a higher order function is a function that does at least one of the following. It either takes one or more functions as arguments, so it accepts functions, or returns a function as a result. So that's pretty much it. It's a function that either takes or returns other functions. This is a very basic example. In this case, we have this call twice function. It accepts any callable object f, and then inside the body, we just invoke the callable object twice. So if I pass something like this lambda that prints out hello to cdc out over here, then what's going to happen is that it's going to be called twice, and it will execute the action 2 times. So this takes a function object, which means it's anything that exposes a call operator. It can be a function pointer even, or a struct with an overloader operator. And in this case, I decided to use a template to implement this, but there are other ways you could do that. For example, a cd function. There are pros and cons. We're going to dive into that later. But the idea is that you have a lot of flexibility on how to do these things in C++. This is another example of the other kind of high-order function. In this case, we are returning a callable object. So we have this greater than function that, given a threshold, returns a function object that compares the argument you give it to the threshold that was specified. So in this case, what we're doing here, we're accepting a threshold over here. we're capturing by value as part of this lambda, and then the lambda is going to return whether or not the argument that it accepts is greater than the threshold. And one way you could use this is in combination with an STD algorithm. For example, countif, you provide a range and then greater than 5 as your predicate, and then this basically count all the elements that are greater than 5. Again, here the implementation is done through a closure, so a lambda expression, and using an auto-return type over here to deduce the type of the lambda. But again, this is just one way you could do it. You could return a STD function, for example, or you could use other techniques such as returning a struct that has a concrete type and stores a threshold. So, question for you. Do we have any high-order functions in C++ standard? Can you give me an example? Yeah, countif. It's kind of cheating, but it's okay. It's too easy. Do you have any high-order function in the C standard? Examples? Qsort, okay. Bsort, beautiful functions, yeah. So in the C standard, we have even more, like obviously you mentioned Qsort, bsearch, and we also have addExit, addQuickExit, and signal. These are all high-order functions. And just to get kind of a different example from the norm, I'm just going to show you signal. And what signal does, it's all kind of weird because it's specified in terms of signal handlers, so it doesn't have a really concrete interface. But it tells you that basically for a given signal, you can specify a handler, and then when that signal is going to be caught in your program, the handler is going to be executed for you. So this is an example of a high-order function because it takes the handler as an argument. And what it says here is that the signal handler must be one of the following. It can be macros for some reason, and then a pointer to a function whose signature must be equivalent to what's specified over here. So it takes an int and returns void. So with that information, you could do something like this. You could include csignal, have std signal. Maybe you want to do something on sigint, and then you provide a lambda expression over here that prints or does anything that might be useful. And the point that I'm trying to make here is that high-order functions are very common in code. Maybe you're used to think about functional programming, but even something like signal handling is a high-order function. And in general, lambda expressions work really, really well with high-order functions and make them usable in modern C++. It is really hard to use them before that, as you have to either create structs or functions, and it's kind of annoying. And finally, stateless closures, like this lambda over here. So lambdas that don't have any capture are implicitly convertible to function pointers. So this is why we can use a lambda with a C standard function over here. In C++, we have a ton of them. You mentioned a few, but literally almost anything from numeric or algorithm, they are likely to be high-order functions. Then we have bind and bind front, which is a new C++20 utility. If you use variants or tuples, you might be familiar with visit and apply. They're also high-order functions, invoke, and even stuff that you can use to basically set a termination handler, like setTerminate. That's technically a high-order function because it accepts the handler for std_terminate. Here's another cool thing. Who here has heard of the erase remove idiom? Okay, a lot of people. So what this does is basically allows you to efficiently remove all the items from a container that match a specific predicate. You can think of it like filtering out some elements. And the way it works is that you use the remove if algorithm with a predicate. So in this case, maybe imagine this some sort of simulation or game where I want to get rid of all the inactive entities. So what I can do, I can specify this lambda over here that says, please remove everything that's not active. And what this will do, it will shift elements around in the range, moving the one that you want to keep at the beginning of the range, and give you an iterator to the last element to be kept. And then once we have that, we can simply call entities.erase, starting from that location over here, which is the iterator returned by removeIf, and then entities.end, and in one shot, it's just going to remove everything that we don't need anymore. And this is quite fast because it just shifts elements around and then removes them in one go without having to reshuffle the vector on every removal. I mentioned variants, so I hope you're familiar with variant. It's really, really powerful too. And what you can do with variants is basically have a choice of a type and then do some sort of compile time switch on it to see what the type is and then inspect the contents of that particular object. So in this case, maybe we have some sort of event loop or event processing pipeline where we could have a network event. It could be either a connection, disconnection, or heartbeat. And then maybe in your event loop, you have this process function that given an event, it visits the internals of this event, checks if it's a connect, disconnect, or heartbeat, and does this kind of dispatching over here where a different action is executed depending on the type that's inside the event. And what you could use std visit for this, and maybe some sort of overload function to create the visitor on the spot, or you could use a struct with multiple variable overloads. But in general, this kind of pattern is a very good use of higher order function, as it allows you to declaratively destructure the type inside of a variant. And if you're more interested in this kind of stuff, I have a talk about ACCU 2017 and Salesforce 2017 when I implement overload and other utilities to basically do pattern matching on variants abusing lambdas. So what are the most common use cases of higher order functions? I would say that probably avoiding repetition is one of them. So it's a refactoring tool in that sense. Then we can invert control flow, and this is probably the most powerful thing about this class of functions. Asynchronicity, and then you can also do compile time metaprogramming. We're going to see some examples of this. So about co-repetition, I would strongly argue that co-repetition almost always leads to bugs and maintenance overhead. There are some people that say, you know, never write an abstraction until you have copy-pasted the code 4 times. I would say, as soon as you copy-paste it once, then you should abstract it away. Because eventually it leads to problems, you forget to update it in one place or the other. So it's always better to avoid co-repetition if possible. Now, in Salesforce 98 and older standards, it was sometimes very annoying to do so, so people were kind of encouraged to not do it. But with new tools like lambdas and high-order functions, way easier to avoid repetition even in complicated scenarios. So sometimes it is trivial to avoid this kind of repetition. So if you have something like this, maybe some kind of integration test where you want to make sure that your routing is working properly. So you set up some machines and reserve a unique port for each machine on the local host, and then maybe do some sort of check that the machines can reach each other. What you could do is, in the first scenario, you could just repeat this invocation of reserve port over and over. So it's not really a big deal, but as you can see, you are repeating the localhost address over and over. And if now you imagine this function gets bigger over time, and people start moving stuff around or adding new machines later on, and then maybe you want to use a different IP for some reason, your code is going to get out of sync, and you're going to have problems, and it's just going to be annoying. So when you features like lambda expressions, I would say it's almost trivial to avoid this kind of repetition. You don't even have to introduce a new function or change the interface of your test. What you can do is simply provide a lambda over here that captures the context by reference, and then simply returns a unique port on that address. And you can call this closure free port, and then use it instead of copy-pasting the thing 3 times. And the advantage here is that since this is basically a local function, it doesn't get exposed as part of your class or text fixture, and avoids repetition, and is basically trivial to write. So I would always encourage you to do things like this. So this is not a higher order function. This is a very simple example of how lambdas can be used over repetition. But the point I'm trying to make is that sometimes it is more complicated to do that. As an example, if you have some sort of structure where there is control flow and it doesn't map to any standard algorithm one-to-one, then you can always avoid this repetition, but you need to do more effort. Like you need to write an extra function, or maybe some utility helpers that are going to be used only for this thing. So you might be discouraged of doing that and just keep the copy-pasting, which I strongly think is a bad idea. In this case, maybe we have some sort of UI widgets, and we're doing an update method, and we want to recalculate the focus, bounds, and update for the children. And maybe in this particular scenario, we cannot do everything in a single for loop because the operations are dependent on each other. So we need to first do the focus, then the bounds, and then the update. And as you can see, we have this pattern where we iterate on the children of this widget. We check that they're visible, and only if they're visible, we're going to execute an action on them. So how would you refactor this to avoid a repetition without, introducing a lot of boilerplate? Any ideas? Yeah? Okay, so what would your lambda look like?
Accepts the lambda and everything else is for the last bit and then.
Okay, yeah. So that's pretty much it. You abstract away the idea of performing an action on visible widgets and accept the action as an argument. So it could look like something like this. You have a local function called forVisibleChildren, which I hope Kate Gregory would agree is a quite descriptive name. And it takes f as your argument, which is not a descriptive name, but that's the action you want to perform on the visible children. And then the control flow becomes part of the body of your function, and the invocation of the action is the parameter that you can customize your lambda on. So in this case, we avoid a repetition, or at least reduce it. And what we do is provide a lambda for each operation we want to perform on the visible children as part of the logic of this function. So we simply say for visible children, autoref c.recalculate focus, and that means please execute this action on all the visible children. One advantage of this is that if in the future you decide maybe to, instead of doing this kind of loop which is not very friendly to the cache, maybe you decide to split the visible and invisible children in two separate vectors, then you only have to change it there. You don't have to change it 3 times. So it is more friendly to future extension and changes to the data layout. Another use case that's probably the most important one is the inversion of control flow. And in general, the example we've seen before is a very simple idea of this. And what we want to express is passing an action or a predicate to a function which deals with the control flow for us. So we want to express what we want to do, but not how. And this separates those two concerns and allows you to have more testable code, so you can test the control flow independently from the actions, and also have some powerful behavior that we're going to see in some examples. In my opinion, the greatest example of this is C++17 parallel algorithms. So what we got in C++17 after standardization is a new set of algorithms where you basically can specify an execution policy as the first argument. And what this allows the algorithm to do is to execute the logic either in parallel or vectorizing, and basically out of order execution or in multiple threads. And this is a great example because we don't really care about how this is executed. Our goal is to execute a function, for example, on every element of a vector. It can be parallelized, it can be vectorized. We just leave that up to the compiler, to the implementation of the algorithm, and we just specify the action that we want to execute. So this is what I mean by inversion of control flow. We are asking, please, you deal with the control flow. I'm just going to tell you what to do. In this case, I can imagine this is a physics simulation or maybe some sort of game that uses physics. And we have these mathematical vectors of position, velocity, and acceleration. We have a vector of these components. And then since we know there is no dependency between all these elements and they can be executed in parallel, we simply ask the standard library, please execute this for each loop in par and seq execution, which means in completely parallel and unsequenced execution, so we're giving the most freedom possible to the implementation, with the entirety of the components range, and then we provide the action, which is simply adding the acceleration to the velocity and then the velocity to the position. So it's moving these particles and performing the physical calculation all in parallel. So the idea here is that we want to decouple control flow from the desired action, and this allows us to test and reuse those two things separately. So we could create a test for the logic and a test for the control flow, and that's it. Another example is printing a comma-separated list of elements. This is something that comes up very often and can get annoying to re-implement the same logic over and over. So we might have an initial version where, we just want to print the elements of a vector out to SDC out, putting a comma in between and avoiding a trailing comma if there's nothing in the vector. So one way you could implement this without keeping state, so any boolean that says if you have visited the first one or not, is by using std empty at the beginning and checking if your range is empty. And in that case, we exit early. If it isn't, we just print the first element without checking anything. So we just print the first element. And then if there are more elements in the range, we iterate from the second one to the end of the range. And for each one, we print out a separator and then the element itself. So this is one way you could do this. And this is a pattern that can come often. Maybe you want to generalize this on other kind of ranges, not just vectors, or maybe other separators. So what I suggest is, if you find this kind of pattern, try to identify the structure and see what is actually the essence of the algorithm. So this is the control flow without the actions. You care about checking if the range is empty and then iterating over the remaining elements. But then you can customize the first action and the separation action. So in this case, the action here was printing, and is the same action over here. And also the separation is what basically puts the comma in between the elements. So all of those things could be parameters to your algorithm. Once you identify the structure, you can create an abstraction for this. In this case, I called it for separated, but I'm sure there are better names, which takes a range, an action to perform on the elements of this range, and then an action to perform in order to separate between those elements. And what we do here is we use std empty in the beginning, as we did before. We print out the first element, and then on the remaining ones, we call the separator action over here, and then the normal action. So f in this case might be printing, and f sep might be separating, but you can customize them to basically have any kind of behavior where you want to iterate by doing something in between each element. So now we can redefine print by using this abstraction, and we can simply say that print is just a call to for separated, which passes the range. The action is printing out an element, and the in-between separation action is just without a comma. And in this case, we get the same behavior as before, but we have this reusable abstraction that provides the control flow and allows the user to customize the actions. And again, if you don't want to test all of these together, so you don't want to do string comparison to figure out if the algorithm is working, you can test for separated separately and then use print to achieve your desired business logic. Does that make sense so far? As an example, maybe if you're writing some sort of quirky command line operation that is supposed to scare your coworkers, or if you want to have some weird text for some enemies in games, you could go crazy and say, okay, my separation action is just printing out a random character, and then it's going to do something weird in between every character you print, and you might get interesting output like this one. But again, the algorithm is exactly the same. We just changed what the separation action is, and in this case, it's just printing out a random character. And I chose this example. It's a little bit artificial, but what I want to show you is that we don't provide the separator as a string or as a character. We provide an action for it. So this allows us to basically have state there and be a little bit more flexible with how we allow the user to decide the logic of the algorithm. This is an example from production code, obviously changed to avoid any copyright issue. Thanks to my worker Marcin for this example. And we did this in some sort of infrastructure broker application. And we basically required to, let me start from the usage, it's probably simpler. We had this unordered set of systems, and a system was basically some sort of monitoring system for a particular node in a network. And what we wanted to do is go through the set of the systems, remove all the systems that successfully initialized, and when we were removing them, we also wanted to execute an action on them to basically step to the next state. So in this case, we say we have all these systems, and we want to check if the system is actually initialized. We call initialize and wait for it to finish. And if it successfully finishes, then we use this state changer function to basically say, okay, you initialize, now you pass to the next state, which is ready to sync. And now, the code before this was basically just a loop in the middle of a big function, and what we were doing was iterating over this range of the map, then checking the predicate, invoking the state changer if the predicate was through. And then we were stepping over this element by removing it from the range by reassigning the iterator over here. If the predicate was false, we were just going forward and finding the next element. So this works, obviously, but if you have this in the middle of a function that's just trying to deal with the business logic of this application, then it detracts from understanding what the application is doing. Because now you have to understand what the algorithm is trying to do, how we're trying to use the unordered set, and also you have to understand what's the intention of the programmer for this particular application. So what we decide to do is create a simple abstraction called consumeIf, and what this basically means is, given a range and a predicate, I'm going to remove all the things that match the predicate from the range and also execute an action on them so that you can perform some sort of cleanup or step to the next state. And then we found other usages for this, and we used this in a few places in the source code. So it turned out to be a useful abstraction. Another use case for high-order functions is asynchronicity. And that's currently the easiest way to basically express asynchronous callbacks. If you think about future or thread, every time you want to compose these things or give the thread an action to perform, you always use a high-order function. However, these kind of things might be superseded by coroutines in the future. Maybe if coroutines get into the language and get mature enough, you wouldn't have to deal with the callback hell anymore, and you can just write code that looks synchronous but is actually asynchronous. But nowadays, as an example, if you want to have some sort of asynchronous graph and get some results asynchronously, combine them, and then execute something else, then high-order functions are a good way to express that. As an example, imagine you have this sort of all function over here that, given a bunch of functions, it executes them asynchronously in parallel. And then when all of them are done, you can attach a continuation to execute an action on the result of those computations. And then you can basically do something like this example here. We do two potentially long requests to the network, getting two images of two animals, and then we wait for the completion of both of them and provide a handler that will expect a payload with both the data of both images, and then maybe we can perform some image processing like stitching this together, and you can extend the pipeline further. So this is code from a library I developed and discussed at SSU 2018 and C++ now the same year, and it's basically a zero location and no type erasure feature library. It's kind of metaprogramming crazy fun, but you can find the same patterns in production-ready libraries, such as STLab Futures by Sean Parent and Felix Perdiconi. And there are proposals in the standard to extend the interface of Future to make it more like Boost Future and allow you to do continuation like this one. So in this case, the idea here is that you declare the shape of your asynchronous graph, and then you leave the execution up to whatever scheduler you want. So it could be a thread pool, it could be IO loop, whatever, but you're performing separation between what you want to be executed and how it's going to be executed. And finally, you can use high-order functions for metaprogramming fun and in general to do compile time algorithms. I have a few articles on this that maybe we can see later if there's extra time, but this is an example of what you can do. This is going to be a little bit interesting. Imagine you want to enumerate a list of types. So if you give it int, float, and char, you want to basically have some sort of Python enumeration, a compile time on the index of the types and the types themselves. And this can come up quite often when you're doing some sort of compile time algorithm, for example, graph algorithms and stuff like that. And if you ask why you would do that, it's a good question. But for example, you might want to have, you've seen this graph over here. This is not compile time. So maybe if you want to do effective scheduling for it, you could do a topological sort on it at compile time and then figure out how to schedule it. So you can do quite crazy stuff. In this case, we want to enumerate int, float, and char, and we provide a lambda over here. And if you've never seen this syntax before, you can actually provide template arguments to a lambda in C++20. So I think this was a proposal by Luis Dion, and this allows to basically have lambdas a little bit closer to normal functions. You can provide a template list, and they're gonna match whatever they get passed if the lambda is invoked through the operator.call. And in this case, I think the code is quite self-explanatory. The lambda will be invoked 3 times, and the first time it will be with int substitute with t and 0 substitute with I, and it will print out 0i, and then 1f and 2c. And similarly, this auto over here is a C++17 feature, which is a non-type template parameter which is deduced. So it can be any kind of integer or anything that's a non-type template parameter. The idea here is that we have a compiled algorithm, and I really see no other way of doing this, because you cannot really write a compile time iterator that is abstracted on the type. So I-order functions are the only way of doing this kind of control flow inversion at compile time. Now I want to look at comparing high-order functions to other abstractions. Or maybe it's better to say other techniques to implement abstractions. And there is a parallel between high-order functions and RAI guards and iterators, and we're going to see why. As an example, this comes up quite often. Imagine that you have some sort of system, and you want to make sure that a part of the system is always accessed in a thread-safe manner. So always under a mutex or under a particular abstraction does that for you. Instead of having like the foo object and the mutex separated and trying to remember all the time to lock the mutex whenever you access foo, what you can do is create some sort of synchronized abstraction that takes a t as a template parameter, and then it only allows access to that underlying t if the mutex is locked. So it prevents you from accessing it without a mutex. Now, this is basically how this will be defined, but we need to define a way to access the contents of foo in order to expose it in a thread-safe manner. And we have a few choices. In this case, I want to show guards and high-order functions. They both work. They achieve the same kind of goal, but there are some pros and cons. So if we use high-order functions, like on the left over here, on the right over here, the syntax will look like this. It would have some sort of .access that takes a high-order function which accepts a foo ref parameter, and then inside the high-order function, you perform the logic that you want. And you might already get what this does, but basically when you call access, it's going to lock the mutex for you, and then after locking the mutex, it's going to invoke whatever function you provided. And this guarantees that there is no way you can access foo without the mutex being locked. Similarly, we can get the same exact behavior on the left if we use some sort of guard, and imagine that calling .access returns some sort of anonymous type object that exposes the arrow operator over here. And when you call the arrow operator, it's going to first lock the object, and then it's going to execute whatever method you want on the object. So it's going to do the same thing in both cases, but there are some differences in usability and how this is implemented. So the guard, as you can see, is friendly to control flow, because if this is part of a function, part of a loop, you can always put a break, continue there, or return there, and it's going to get out of the function where this is actually being executed. However, if you do the same with a high-order function, you cannot really put a break inside the high-order function or a return inside the high-order function, because that is scoped to that particular closure and will not affect the surrounding control flow. So if you have that inside of a loop and then you want to break, that doesn't work. You cannot do that. Also, high-order functions might require captures. So in the first case, if we want to access this and then maybe invoke some method passing some object that's on the stack in the surrounding context, we can do that without any problem. But in this case over here, we might have to capture the object. And that's usually not a problem, because you know that the scope, the lifetime of this lambda over here will always be inside the access call, so you can always capture by reference safely. But it's still a capture. It might prevent optimizations, and it's still an extra step you have to take in order to achieve the same result. So why would you ever do the thing on the right compared to the thing on the left? Well, there's a very important point, which is simpler implementation. Implementing the thing on the right is trivial. while implementing the thing on the left is a little bit more complicated. I'm going to show you why. So this is how you would implement the guard object. We would basically have this synchronized abstraction, which has our object and a mutex. And then we have this access function that returns our guard by value. And the guard is probably some sort of type like access guard, which contains a lock guard, and then exposes an operator arrow in order to access the data that's inside the object. And now this doesn't even fit on the slide because you might need a constructor to initialize the guard. You might want to prevent moves and copies. So there's going to be significant boilerplate to achieve this kind of result. Then you finally return it, and the user is going to be able to access the object for the arrow operator. In comparison, if we look at the high-order function version, it's super simple. What you're going to do is basically have this access function. It takes an f parameter, which is your action. Then it locks the mutex for you and just invokes the action on the object and returns whatever result you want. And that's all you need to do. It's 2 lines of code. It's quite easy to understand and to review. And my argument here is that you're kind of making a trade-off between ease of implementation and ease of usage for the final user. Also, if you want to impress your coworkers and get fired, you can also use the comma operator over here. And what this does is basically prevent you from having to write a name for the guard and guarantees that the guard will live long enough to execute the action on the object, and it just saves a line for no reason. Another example of this is benchmarking a function. I'm not going to go through all the steps, but sometimes maybe you want to write a super micro benchmark without importing Google benchmark. You want something quick or just print out how many seconds it takes to run something. So one thing you can do is write a benchmark function. It takes an action f. Then we use chrono to get the time before we call the function. We call the function, and then we use chrono to return the interval in which the function was invoked. So this is the world's stupidest benchmark, but it can be useful. And again, this is implementation with a high-order function, but you can do the same with a guard. You can imagine having a guard that stores the initial time as part of the state, and then in the destructor of the guard, you compute the difference of the time and perform some sort of action or time collection. And again, there's this trade-off of what do you want to do? Do you want to have a syntax that allows you to deal with control flow in the surrounding context, or do you want a simple implementation like this one? I don't have a good answer for that. Now, another abstraction that we can compare high-order functions to is an iterator. And as an example here, I want to iterate over a filtered range. So maybe I have a range of integers, and I want to iterate over all the even integers. So on the left, we can see that by using some sort of iterator and some sort of range, we can basically achieve this with a range-based for loop. We can say for int x in filtered ints with even, where even is some sort of predicate, so some sort of lambda that just filters out the odd ones. And then we can perform our action in the body of the loop. So this is friendly to control flow again, because we can break out of the loop immediately, or we can continue, or we can return from the underlying, from the surrounding scope. It's more composable with STD, because filtered must be some sort of range, so there must be some sort of filter iterator, and you can use that with STD algorithms. But the implementation gets even more complicated compared to guards. On the right-hand side, we can see the same idea using high-order functions, and in this case, we have, again, our vector of ints, and then we have this for-filtered function, this kind of algorithm, where you provide a range as the first argument, then your predicate maybe is even, and then an action you want to perform on all the elements that match the predicate. So this will have a very, very simple implementation, but again, it might require you to capture things inside a lambda, and it might be unfriendly to control flow. If you return inside a lambda, that return is going to be local to that function, it's not going to return outside of the surrounding context. So why do I say this is complicated? Well, Boost provides filter iterator, which is exactly what we want, is some sort of iterator that given a predicate skips over the things that don't match the predicate. And as you can see, you need to do a lot of boilerplate, a lot of extra work to implement this. So you might want a lot of constructors, you might want to expose the iterator traits, and make sure you have end, begin, and dereference operators, increment, and so on. It takes a lot of work to create something conceptually simple. Fortunately, Eric Niebler just standardized ranges, so we're going to have a lot of this abstraction in the standard library implemented for you. But for the people that just need something quick and simply want to make the business code a little bit nicer and focus on the logic instead of how the logic is performed, this is too much. Like, you wouldn't pass code review for a filter iterator if you don't know you're going to use it in 100 places. However, I argue that using a higher order function gives you a chance to maybe make your code a little bit nicer, make your logic more obvious for a very small cost. So in this case, the implementation of that is literally 3 lines of code. What you're going to do is provide full filtered, which takes a range, a predicate, and a function. And then inside for filtered, you're going to have your logic where you iterate over the range, check the predicate, and then call the action on the object if the predicate is valid. And that's all you need to do. It's very simple. It's very easy to review and understand. And in the right places, in the right context, it can help the readability of your business logic. So as a recap about higher order functions, they're very powerful. They have many different use cases, and they are easier to write than existing alternatives. And I'm suggesting to do that when you need some sort of quick, testable, and reusable abstraction that doesn't have to be very composable or super mature as part of a foundational library for your company. In that case, I think they're great and they're better than the alternatives. And also you can see that the language might provide better alternatives as well. We're going to have ranges, we can have coroutines for asynchronicity. So these higher order functions are really powerful, but sometimes they're not the simplest abstraction to represent something. And the language is trying to move towards better alternatives. They don't play nicely with control flow on the color side, because if you have return, break, or continue in the lambda body, that's not going to be used in the surrounding scope, just going to be local to the lambda. They get even more powerful in 17 and 20. In 17, we got context per lambdas, so you can have these compile time algorithms. And in 20, we have the template syntax for the lambdas, so you can have that kind of extra feature as well. There are some proposals that might have helped. Unfortunately, the ship has sailed for those. This was a proposal by Barry Resvin about abbreviated lambdas for fun and profit that introduced something like the arrow function JavaScript syntax in C++. You've all seen Patricia's talk yesterday about how C++ and JavaScript are getting almost the same. And this would have been nice. We would have very terse lambdas, making this more accessible, but unfortunately for some reasons it didn't get in. So my point is another problem with this is the verbosity of lambdas. In C++, they're very verbose, like capturing things explicitly and having the boilerplate of the parentheses and stuff like that. It can really detract from readability compared to other languages like JavaScript or functional programming languages. Okay, we're going to move into function ref. Any questions so far? Yeah. So is there a recommended design pattern if you want to return from a higher order function to the outside? I don't think there's anything that's recommended, but what you can do, you can simulate breaking and continue by returning some sort of enum that is like want to break, continue, or do nothing. And then in the implementation of the higher order function, if it's like a loop, you check the return type, the return value of your action, and then do the break and continue there. But that kind of makes it more complicated, so it defeats the purpose a little bit. So if you find yourself doing that, maybe you want to write an iterator, for example. But there are definitely ways you could do that. Yeah?
How do you find the balance between, it's very good to find the higher order functions and then just passing the lambda, but the lambda will have some sort of business logic, which probably you might want to get unit tests for. How do you find the balance between, oh, this is a lambda, or I actually need to take this out? And
okay. So the question is, how do you find the balance between using a lambda and basically full-fledged function with a contract and stuff like that? I think there is no objective guideline on this. It's mostly on your engineering sense and common sense. If it's something really simple like filtering out even integers, you probably don't really want to have a function with comments and stuff like that. Everyone knows what percent sign 2 does. And it's very short. It doesn't really warrant an extra function. But as soon as it gets tricky, as soon as you have preconditions, I would say as soon as you have preconditions, as soon as you have logic that's not trivial for most people to understand, then it might be more beneficial to have a function with a contract and unit test that. Note that you can also have a lambda outside, so you could have something like a const lambda as part of your namespace or class, and then unit test that as well. It's still possible to do that, but in general, if you find yourself thinking maybe I should unit test this, then you should. Let's put it that way. Any more questions? Cool. So let's move on to function ref. So what options do we have to implement higher order functions? I've been using templates throughout the talk, but that's not our only option. So one thing you can do is use a pointer to a function. It's very C style, but if you have this operation, higher order function, and you want to take an action F, then you could use a pointer to a function. It's the simplest and most C-like way to do this. So this works with non-member functions and stateless closures. It doesn't work with stateful callable objects. So if you have a lambda that captures something, then you can't convert it to a function pointer. It has very small runtime overhead, and if it's in the same translation unit, it's easily in line that a compiler can see through this. And one important thing compared to templates is that this is constrained with an obvious signature. So you can see it returns an int, and it takes 2 integers, which is something you cannot see if you use a template parameter without a sphinx. Another option, as we've been saying, is template parameters. In this case, we take an arbitrary f, or that should be t, that's a typo, but you take an arbitrary type, and in this case, it works with any function object callable if you use std invoke, so even pointers to member functions. It's a zero-cost abstraction if you think about runtime, because the compiler can see through the template, it's going to be in the header, so it's super likely to inline it, it's super likely to just ignore all the craft and stick your operation right in your business logic. It's hard to constrain before C++20, so if you want to make sure that f has a particular signature, then you need to do something like enable if is invocable of int and so on, which defeats the purpose because the declaration is going to be bigger than the body of the function. But in 20 we have concepts, so you might be able to just get away with a simple concept using something like invocable auto f, where you specify the signature. So that might be a better option in C++20. And this is an important thing. This might degrade compilation time. If you use this all over the place compared to a type erasure wrapper, then you're going to instantiate more functions, and this can make your compile time suffer. And as an aside, you cannot also use this in virtual hierarchies, because you cannot have a virtual template function and have other people override from it. Then we have std function. It works with any function object or callable. And it's easy to constrain. You see the signature over here is very obvious. However, this has very significant runtime overhead. And it's super hard for the compiler to inline and optimize. There are a few reasons for this. The first reason is that this is an owning wrapper. So it owns the function you give it and stores it inside. And this means that if the function object is like a lambda that captures 400 integers, it needs to allocate memory for that. So it can allocate, it owns the object, and as an optimization, it also uses the small buffer optimization. So it's like std string. He has a small internal buffer for small closures. And all of this is good in the general case, but it adds complexity and prevents the compiler from seeing through the abstraction and inlining it. So all this complexity prevents this from being inlined in most of the cases. Also, this has unclear semantics. I said it's owning because it's owning 99% of the times, but if you construct this, for example, with a reference wrapper, then it's going to act like a reference. So depending on what kind of thing you construct the function with, it can have reference semantics or owning semantics. And this is not a problem usually, but we would like our signatures to explicitly tell us what ownership semantics they have. And in this case, it depends on the runtime, not on the signature. It also has other problems, but I'm not going to cover those. Finally, we get to function ref. So this is what I propose for C++20. And it works with any function object or callable, so it's just like a cd function in that aspect. It has very, very small runtime overhead. It can easily be inline in the same TU, and I'm going to show you benchmarks. It is constrained with an obvious signature, so you can see it returns an int and takes two integers. And if you pass a function that doesn't have that signature, it's going to give you a clear compile error, not template spaghetti. And it has clear no known in semantics. So this is a function ref. The word ref tells you I don't own anything. I'm just a reference to a callable. And it's very lightweight. So the parallel I like here is think about this as string view for callable objects. So you have, it's not going to own the callable. It's just going to be a view over it. So in a nutshell, this is how you use it. You provide the return type and the arguments as part of the declaration. It is a non-owning reference to any callable. And the parallel, as I said, is std string as string view, std function as function ref. That's the way you think about it. It doesn't own or extend the lifetime of the reference callable. So this means that if you give it a temporary, and the temporary doesn't live long enough, then you're going to have a dangling reference. But it is lightweight, it's no accept as much as possible, and optimization friendly. I proposed this in the paper that you can see there, and it's currently in LWG, which means it passed design review, now it's on to wording review. And many thanks to the people you see on the slide, they helped a lot with the paper, and without them, it haven't been possible. This all started because Eric Niebler tweeted, "We need function ref. It's been implemented in LLVM code base, GC code base, but should be standardized." And he said, "This is a paper that writes itself." No, it's not like that. I said, "Yeah, I'm going to do it. Easy paper." Nah. But it's been fun, and I learned a lot, so it's been a really great experience for me. So, in practice, why would you use function ref instead of std function? So if you care about performance and you want clear reference semantics, then you should always use the former where possible. So sometimes you need a std function because you actually want those ownership semantics. Maybe you want to store everything in a vector of functions, or maybe you want to pass it to an asynchronous callback that doesn't guarantee it's going to live long enough. But if you just want a callback, so something that is executed in the same stack frame, then function ref is what your choice should be. And also it gives more clarity to the reader of the code because they know this thing is not going to be stored, it's just a reference. And why would you use function ref instead of template parameters? So function ref is easier to write, read, and teach. The compile time error are better. The signature is right there in the function, and it's simpler. And you can use this in polymorphic hierarchies. This is something we've been doing in our code base. And basically, you can have a virtual function that takes a function ref, and then you can override it, which is great. And all of this also ends up making compilation time better because you have less instantiations, you can implement these things into source files, and you can use type erosion and virtual hierarchies where performance is not critical, but you still want to avoid extra compilation overhead. So this is the synopsis of the class, and as you can see, it's basically just a wrapper around an object pointer and a function pointer that tells you how to invoke the object. It has a constructor, copy constructor, then a constructor from any callable. Obviously, this one is simplified. There's going to be some sphinx there to avoid conversions from signature that don't match. Then you can copy it, copy assign it. You can target it to a different function. You can swap, and you can invoke it. And as you can see, the invocation is always const because the function ref itself is just a reference. It's never going to be modified, so we can do that on a const reference, and it's going to be conditional no accept depending on what you specify in the signature. So it also supports no accept signatures. Okay, so I'm going to skip to the benchmarks because I think that's the most important thing, and then if we have time, I'm going to show you some examples and implementation. So in order to benchmark this against the template parameters, std function, I used quickbench.com using Simon's brand is functional implementation, which is quite good, and he's at the conference. I'm not sure if it's in the room. Internally, Quickbench uses Google Benchmark, and my scenario was to invoke a simple higher-order function in a loop. And I also want to test with and without inlining what difference it made. So it's something like this. I have a version taking a template parameter, which calls benchmark do not optimize with that thing. SCD function, the same thing, and function ref, the same thing. And if you have never used Google Benchmark before, do not optimize basically forces the compiler to not remove the code. It basically makes the compiler assume that thing is going to have a side effect. So it gives you a realistic way of benchmarking something simple. And then I did the same with no inline. So I just added attribute no inline on every test case. And then I run it with some sort of test like this, where I simply pass a lambda returning 1 in a tight loop that's going to be called millions of times. So that's what Google Benchmark does for you. So all I want to measure here is the overhead of creating the high-order function parameter and invoking it. So this is what I see. With GCC 8.x, using optimizations and lim and C++, if everything is inlined, then template parameter and function ref are completely the same. So as long as you're in the same TU, or as long as you have LTO and things get inlined, then function ref is going to be equivalent to a template parameter. Now, if we don't have inlining, then a template parameter gets a little bit 3.5x slower than an inlined one, and the function ref, which is not inlined, is about twice as low as the non-inlined template parameter. In between, we see an inlined SCD function. So the blue one is SCD function with inlining, and it's 7 times lower than both function ref and template parameters. So that's the overhead you pay for if you have a tight loop where you call SCD function. If you don't inline SCD function, it can get up to 11 times slower. And I tried with Clang, with both lib standard C++ and lib C++, and the results are very similar. So you can always see that the first two are equivalent. SCD function is at least 7 times slower, and then by removing inlining, it just gets worse, but SCD function is still the slowest of them all. So in general, when inlining happens, function ref is always as fast as the template parameter. SCD function is at least 7 times slower than function ref. In some tests, it got 8 times slower. When inlining doesn't happen, function ref is around 2 times slower than a template parameter, but SCD function is still 1.5x slower than function ref. So there is still extra overhead that you use for SCD function in that case. So my conclusions are that function ref is optimizer friendly and thrives with inlining. It's super simple to implement, and the compiler can see right through it. And it is always faster than SCD function. So if you don't need ownership semantics and you want to, make your code generally more performant, then you should prefer it to SCD function when appropriate. As my conclusions, any function that accepts or returns an order is a higher order function. You don't have to go full functional. You can use them in few places to make your code a little bit better. We have very varied use cases, and they're highly usable thanks to lambda expressions. And they are easier to implement compared to other alternatives that we've seen, like RII guards and iterators. And again, my point is, you don't have to embrace the full Haskell style. Sometimes in your code, you can find opportunities to use this kind of abstractions without changing the paradigm and making it still accessible to new hires and new people. And function ref is just an unknown reference to a callable with a given signature. Hopefully, we're going to have it in C++20. It's very lightweight, and you can start using it today. You can either look at the proposal and implement it yourself. I think it's going to be a great exercise. Or Simon Brand has an implementation on GitHub over here, which should be very compliant to the paper. So thanks. I have a few minutes for questions. Yep.
In cppcon this year, people from Houdini engine showed that they inherit their string implementation from their string view implementation. Have you considered that for function ref and function?
So the comment is that people from Houdini showed us at cppcon that they inherited their string implementation from string view implementation.
Yeah.
Have you considered this? I need to see why they do that. Is it just to avoid code repetition, or is it?
No, you can then pass your string to a function that accepts string view without any error.
Ah, okay. So it allows you to convert the string to the string view. I have not considered this. Might be interesting, but I think it's too late to change how SCD function is defined, because if we introduce a base class that's a function view, then it would break ABI, as far as I understand. But it's an interesting thought. No? No, but people do, and if the standard if the standard doesn't, then people won't consider the standard. Let's put it that way. But it's an interesting thought. I'll think about it. Any more questions? Yeah?
So you keep the same const behavior as std function, right?
Yeah.
So it's broken.
Okay. So the comment is you keep the same const behavior as std function, so it's broken. std function is broken because if you don't know, std function has unconditionally cost qualified operator call. So for example, if you pass a mutable lambda inside an std function that changes its state on every call, then you can invoke that through a const std function, which is very weird because you're saying the std function owns the lambda changes its state, maybe as a counter internally, and then if you call it through a const std function, it still compiles. So it's very counterintuitive to me because it's not a reference, but for function ref it makes complete sense because references are always const, and the constness applies to the reference itself, not to what's being referenced. So in this case, function is broken, function ref isn't, even though they have the same signature. So the comment is there's a function pointer.
This is a function pointer then. Const reference, const t star, const t reference is const. Like you can't modify it
Yes.
through const reference.
Yes. So another thing that function ref supports is you can put const as part of the signature in the function ref, other than no except, and that will enforce that the reference callable is const qualified. So those are things that were proposed for a std function, but they never got fixed because it's too late to do that. There's too much code depending on std function. But I think that the function ref behaves in a sane manner in this particular case. Yep.
In your slide you passed function call result to do not optimize.
Which one, sorry? This one? So this is a utility from the Google Benchmark library, and it uses some assembly magic to basically force the compiler to not optimize away the call to f. So the way I like to think about it, it makes the compiler assume there's going to be a side effect when you call that function, and it prevents it from being thrown away. And in this case, we need it because, as you can see in the lambda, we're literally doing nothing. We're just returning 1. So the compiler would just say, you're doing nothing, there's no side effect, this is a no-op, and just remove everything. So that's one way to do it. Sorry? It's a Google benchmark feature. Yeah. Yeah.
We've seen function ref being used as a parameter in a function.
Yeah.
Is it also, as long as I'm being sensible about lifetimes, is it also reasonable to use it as a data member in a class like I might use reference wrapper?
Okay. So this is a very interesting question that you asked it. And the question is, we've seen it being used as a function parameter. Is it sensible to use it as part of a data member or somewhere else? And there can be good use cases, but you need to be really careful because it's the same as storing a string view, it's the same as storing a pointer in your data member. And since everyone is very used to std function, they might not realize they're storing a dangling reference. So these are some slides about pitfalls. If you see here, for example, a function ref that is called getNumber and initialized from a lambda, and then you call it, what do you expect to happen? Okay, that's an expectation, but it's wrong. So, what else? Maybe. So? So the lambda is a closure object. Is as an instance of a temporary closure object, and the function ref is referring to the temporary instance. But the temporary instance goes out of scope as soon as you reach the semicolon. So when you invoke the get number over there, it's going to be a dangling reference. The lambda doesn't exist anymore. So this is a very important pitfall you need to understand about function ref. And it's not really a pitfall, it's if you have a pointer to a temporary, obviously the pointer is going to be dangling on the next line. But it's the same principle with function ref, is just a reference. So it's not going to extend the lifetime of something.
If you explicitly cast it to a function pointer, will it work?
No, there's another pitfall, but there's some discussion there. So if you have something like a function pointer, in this case, because of the way function ref is currently defined, it is simply going to take a reference to the pointer itself. Because the pointer is a callable by the standard terminology, so it fits the callable concept. So this is referring to the pointer. And the pointer, is a temporary, so on the next line is going to disappear. And there's been discussion about this, and maybe LWG is going to make me change it. But the point here is that we could do this safely for normal functions. We could just store the function inside the function ref. So this would work with a free function like getNumber. We could make this work. But then we would be inconsistent with pointers to member functions because those are bigger than normal function pointers. And to make that work with pointers to member function, we would need a bigger function ref. And we don't want to do that. So, yeah. Yeah?
In the previous slide, so if we add, maybe, if we add a plus in front of the lambda, it's converted into a pointer function?
Yeah, so
it's a pointer function, so it's strictly equivalent to the other slide?
Yes, exactly. So the comment is if you had a plus before the lambda, it forces a conversion to a function pointer, which makes it equivalent to the second slide. It is possible that this might become defined behavior, but I wouldn't count on it. And I don't think it's a very compelling use case for function ref. Let's put it that way. Yes? It is copy assignable, yes. Oof. So if you see the synopsis, I just want to make sure it is trivially copy destructible, trivially copy constructible, and trivially copy assignable, and is not going to be called function view because view has a very specific terminology in the ranges standard library, and it means a range, like a non-modifiable view over a range of contiguous objects. So that's why it's called string view, because it's a range of contiguous characters. But in case of a function, it doesn't make sense. And the first revision of this proposal was called function view, but it didn't really pass design review. Yeah?
Does it work together with cross template argument reductions, or should I specify it's something or can I just do function reference?
So the question is, does it work with class template argument reduction? Yes, there are some reduction guides that I excluded here. You can see them in the paper. But it should do the best possible effort to deduce a lambda. So if a lambda has, it's not a template lambda, it's not a generic lambda, you should be able to deduce it. And for functions, function pointers, that should all work. That should be fine. Any more?
Well, I suppose a simple one then. Do you see it as best practice then that if this gets in, that basically wherever we've been taking a function as a, for a Boolean reference or something, we basically just change everything to use this?
Okay, so the question is, what should be the best practice in case this gets standardized? Should we always use this instead of template parameter or STD function? I would say no. It depends on your use case. So first of all, if you use a template parameter or STD function, that doesn't mean that it's not going to be stored somewhere. Like if you take a higher order function that takes a tref, then the body of the higher order function could make a copy and store it somewhere. And that wouldn't work with function ref because it's just a reference. And it's the same principle for a STD function. But what I would say is, in general, whenever performance is a concern, but not too much of a concern, you want to use function ref instead of a STD function and instead of template parameters, as long as you have reference semantics. Because you're going to have better compilation times, you're going to have better errors, better code, and the performance is going to be great, especially if you're inline. But if you're writing something like standard library algorithms, you want to make sure that this thing is always inlineable, always as fast as possible. So in that scenario, you might still want to use a template parameter to ensure that the compiler has full freedom of optimization over that particular thing. So I would see this more as a hierarchy. You have the template parameter when you have a super low level abstraction that has to be, visible to the compiler in its internals. Then function ref for anything that's reference semantics and needs to be fast without, it's always going to be as fast as a template parameter, it's going to be inlined. But in the case it's not going to be inline, it's going to be a little bit slower. So that's the second step of the hierarchy. And then you have STD function for expensive owning wrappers. So that's the way I see it. And I think there's a lot of use cases that fall in the middle, so function ref will have a lot of use cases. Yep. So the question is, STD function is very liberal in the way it accepts signatures matching the one you specify, for example, conversions and stuff like that, is a function of the same. So it is defined in the wording as, you have this signature and it accepts anything that's invocable with that signature. So you need to refer on how is invocable is defined, which uses the invocable concept. And I think in general, a good approximation is if I can call this thing by providing those arguments, like a function call, and it compiles, then it's considered invocable. So it should cover implicit conversions and anything that on that line. Cool. I think I'm running out of time. You can find me later if you have more questions. Thanks everyone for attending.